Hello everyone, I'm here today to present you a paper we have published this year in Neural Computation. The paper is entitled A Robust Model of Gated Working Memory. In this paper, we propose a model for working memory. But what's working memory? Let me show you what it is on an example. Are you ready? Let's go. Please count the dots. Please count again the dots. Now, let me ask you a simple question. Were there more dots in the first picture or in the second one? There were 10 dots on the first picture and 11 dots on the second one. So the answer is clear, there were more dots on the second one. Let's now look at what you have done to answer that simple question. On several occasions, you had to remember numbers in your head. For instance, while you were counting one by one the dots, 1, 2, 3, 4, etc., or when you had to compare the number of dots, 10 and 11. Actually, when I asked you to compare the number of dots, there were no more stimuli allowing you to find what the numbers of dots were. You were maintaining these two numbers in your head. And that's precisely the role of working memory, to temporarily maintain information about stimuli in the absence of these stimuli. In the example I have shown you, you had to maintain numbers, but many other types of information can be maintained. And in the brain, most of the cortical region seems to play a role in the maintenance of some type of information. For instance, in the lateral prefrontal cortex, one can find information about frequencies. Let's take a look at how the brain maintains those frequencies. So here is an example of task performed by monkeys. The task is very similar from what I have asked you to do in the beginning. The monkey has a vibrotactile device in the hand. At some point, this device will vibrate at a frequency f1 for half a second. It will stop vibrating for 3 seconds, and vibrate again at a frequency f2 for another half a second. And in the end, the monkey has to say, by pressing buttons, which of the two frequencies was the highest, the first one or the second one. Here is how looks the firing rate of the neurons in the lateral prefrontal cortex. From these, let me highlight two properties. First, working memory is coded in a distributed way. There is not a single neuron coding for the memory, but many. And second, the activity of the neurons coding working memory can vary in the delay. That means that these neurons might not display a full sustained activity. Actually, in this paper, they even show that the coding of the memory rotates. Let me summarize the three empirical findings I mentioned. 1. Many types of information can be maintained in cortical areas. That suggests that there could be a generic underlying mechanism. 2. Maintained information seems to be distributed among some neurons. And 3. Those neurons don't necessarily display a sustained activity. The question we asked ourselves was then, can we design a generic neural mechanism for maintaining information in a distributed way and without any sustained activity? And the answer is yes. Let me go through it. In our paper, we propose the generic mechanism to be a gating mechanism. The idea of gating is the following. Imagine you have a flow of data. Imagine you have a room that contains what you remember, and imagine that the flow of data enters the room through a gate. What you want is to remember a few elements from the flow of data, and the gate is what's going to help you doing that. When the gate is open, the flow enters, and you update what you remember. When the gate is closed, the flow is blocked, and you maintain what you remember. In this work, we didn't make any assumption on how the memory is actually coded in the room. In fact, we propose to find the coding through learning, and we expect the coding of the memory found to change over time. The only requirement we have is that, when the memory is needed, it must be possible to decode it. In order to learn to perform gating, we designed several gating tasks. For the sake of simplicity, let's focus on the simplest of them. In this task, the model receives two inputs, a flow of data that are real values between -1 and 1, and triggers that are binary 0-1 values. Triggers are what will control the opening of the gate. When the trigger is on, the gate opens, and when it's off, it closes. In this cartoon, real values are represented as colors varying from purple to yellow, and binary values are represented as black for 1 and white for 0. In this task, the information will be directly maintained in the output. So, when there is a trigger, the output will have to update its value to the new data coming, and keep it till a new trigger is received. Let's describe it on the example. In this example, the time flows from left to right, and on the first time step, the model receives a trigger with an orange data. So, The output is updated to the orange data. This orange data is maintained till a new trigger is received. Later, a new trigger is received with the yellow data. So the output is updated to the yellow data. This yellow data is maintained till a new trigger is received, and so on and so forth. In this work, we propose to use a reservoir model to solve this task. More precisely, we use echo-state networks. Echo-state networks are recurrent neural networks with three layers: an input layer, a recurrent layer, and an output layer. The specificity of echo-state network is that only the weights from the recurrent layer to the output layer are trained. The other ones are randomly sampled in the beginning and left unchanged. In fact, because only these weights are trained, there is no need for any backprop or backprop through time algorithm. Only a linear regression can be used to train. In the paper, we use a pseudo-inverse to perform the linear regression, but we also have tried online ridge regression with the force algorithm, and the results remain the same. In our model, as information needs to be maintained for a long time in the output, we also consider feedback connection from the output layer to the recurrent layer, and these connections are also not trained. Here are the different variants we considered. In A, it is a gating task as I described earlier. In B, the model receives several triggers that controls its own output, so the model has to maintain simultaneously different values. In C, the model receives additional stream of data that have to be ignored. Only the first stream of data is relevant. And in D, the data are no more real values, but visual representation of numbers. And it is the values of the numbers that have to be maintained. Long story short, all these tasks can be performed by a reservoir. In A, we see what happens for the simplest task of gating. In gray is represented the stream of data. For better visual representation, it has been smoothed. Dots in the bottom represent the trigger, and the black line represents the output. We can see that when there is a trigger, the output copies the input it receives and keeps it till the next trigger comes. In B, we see what happens when multiple information, or more precisely 3 information, have to be maintained simultaneously. We can see that some of the output can drift slowly. Actually, the more information have to be maintained simultaneously, the more likely it is to drift, and the faster it will drift. In C, we see that additional disturbing stream of data have no influence on the maintenance of information. And finally, in D, we can see that even though the value to maintain are quote-unquote hidden, they can be extracted from the visual representation of the numbers and maintained. From now on until the end of the talk, we will focus on the simplest task. Here we show how the performance of gating depends on the 6 parameters of the reservoir: the spectral radius of the recurrent weight matrix, or its maximum absolute eigenvalue, the leak rate, equivalent to an inverse of time constant, the number of units in the reservoir, the sparsity of the recurrent weight matrix, the scaling of the input weight matrix, and the scaling of the feedback weight matrix. On these plots, only one of these parameters is changed at a time. The other ones remain the same. The default values are represented by a star, 0.1 for the spectral radius, 1 for the leak rate, corresponding to no leak, 1000 for the number of units, 0.5 for the sparsity, and 1 for the input scaling and the feedback scaling. We can see that there is a wide range of parameters where the gating works. In short, it works as long as there is enough neurons in the reservoir, as long as the spectral radius is not too big, and as long as the input and feedback scaling are neither too big nor too small. Now that we see that values are maintained, the question is, how are they maintained? Here we show how values are maintained when there is no inputs disturbing the system. Let's focus on the B plot in the middle. On this plot, each black line corresponds to the output for different initialization of the value that is stored, and these values are uniformly spread between -5 and 5. We can see that for initial values outside the range -1 and 1, the output ultimately converges towards 1 or -1. But for values between -1 and 1, the memory remains, at least for hundreds of time steps. In C, we compare the values stored after 500 time steps and the initial values. On this plot, we can precisely see that the drift occurs only for values outside the range -1 and 1. In D, we show the distance between the states at the time of the dotted line and at the end. This is meant to show that when there is no input, the reservoir activity stays on a segment, and each point of this segment is associated to a value between -1 and 1 that is stored. So, in other words, when there is no input, there is a kind of approximate bounded line attractor, or segment attractor. Here is what happens when we change the spectral radius. This plot is the exact same than before, but with a different scaling on the D plot. When we increase the spectral radius from 0.1 to 0.5, some values between -1 and 1 start to converge towards the same outputs. It is as if the line attractor became discretized. And eventually, when the spectral radius is 1, only two discrete values remain, -1 and 1. What happens now when there is input? On the bottom plot, we show the behavior of particular neurons. Neurons that display a sustained activity that is correlated to the output. To identify these neurons, we select the 20 most correlated neurons with the output. Here are the neurons displaying sustained activity in the variance of the gating task. In A, for the simplest task, we see that many neurons display this sustained activity. However, in B, C, and D, we see that there are less or even no neurons with this sustained activity. Actually, in C, when additional irrelevant inputs are added, we see that the neurons that display a sustained activity strongly oscillates because of the inputs. The question is then, are neurons displaying sustained activity essential at all? In fact, we can show that the neurons displaying a sustained activity are not essential to decode the memory. In this plot, we show the performance of the decoding of the memory from a subset of neurons. In orange, we select the neurons in ascending order of their correlation with output, from the most correlated to the least correlated. In blue, we select the neurons in descending order of their correlation with the output, from the least correlated to the most correlated. And in black, we just take random ones. We can note that even in the worst case possible, the blue line, only a few dozens of neurons are enough to decode the memory with a similar precision than in the best case, the orange line. In other words, the memory can be found even without the neurons displaying a sustained activity. Or, more generally, as long as there are enough neurons to decode from, the memory can be found. In fact, we can go even further and make the neurons displaying a sustained activity disappear. The idea is the following. Before, we have seen that additional disturbing input makes strongly oscillate the neurons displaying a sustained activity. The idea is therefore to increase the disturbance of the inputs. In practice, it is done by changing how the input weights are sampled. In the initial behavior of the model, these weights are randomly sampled uniformly between -1 and 1, and therefore they can be close to 0. The idea is to prevent the input weight from the stream of data to be close to 0. In the bottom plots, we sampled these weights between -1 and -0.5, or 0.5 and 1. In absolute values, these weights would then be at least 0.5. In the C plot, we show how the gating can still be performed. In the D plot, we show how look the most correlated neurons with the output, and they are not correlated at all. In summary, in this slide, we show that even to maintain a memory, the sustained activity is not necessary. Then, how is it possible to explain what the model uses to maintain? In the paper, we have done it by making a model of our model. We simplified the reservoir model into a 3-neuron model. On top, you can see how these 3 neurons are wired. This reduced model has 2 parameters, A and B. A is assumed to be big, and B is assumed to be small. On bottom, you can see how behaves these neurons. X1, that receives only the stream of data V, copies it. X2, that receives both the stream of data V and the trigger T, copies the stream of data and saturates to 1 when there is a trigger. And X3, that receives both the feedback from the memory M and the triggers T, copies the memory and saturates to 1 when there is a trigger. Let's see more in detail why this reduced model works. Let's look at what happens when there is no trigger. When there is no trigger, T equals 0, and therefore everything happens as if there were no connection from T to the neurons. Now, if we look at X1 and X2, they both receive the exact same inputs and have an opposite contribution to the output M. Therefore, they compensate, and the contribution of them both in the output is null. In the end, everything happens as if there were only the loop from X3 to M. Let's look more closely at this loop. V small b ensures that the neuron X3 behaves in its linear regime. So, X3 copies its input. Therefore, X3 is going to be b times M. And as the output weight from X3 to M is 1 over b, X3 ensure that M remains constant. Let's look now at what happens when there is a trigger. When there is a trigger, t equals 1, as A is big, and because of the tangent hyperbolic activation function, both X2 and X3 are going to be close to 1. In other words, they both saturate to 1. Moreover, as I have an opposite contribution to the output, they compensate. So, everything happens as if only the feed-forward connection from V to X1 to M were present. Moreover, similarly than before, the will be ensured that X1 behaves in its linear regime. So, X1 copies its input, and therefore, X1 is going to be B times V. And as the output weight from X1 to M is 1 over B, X1 ensures that M is copying the input V. Actually, this model displays an interesting behavior even if A is not big. Here we show the behavior of the reduced model for different A and B. On the right column, we can see that B directly controls how fast the memory is going to be forgotten. On the left column, we can see the influence of A when B is small. Instead of maintaining the correct value, it will mix the new value to maintain with the previous value that was maintained. And A will control how the mix is done. It is precisely what does the update gate in a gated recurrent unit. That shows how, with few regular neurons, it is possible to mimic a gated recurrent unit. Let's come back to the reservoir model. We used the reduced model to explain what was doing the reservoir model. But how? In fact, in the reservoir model, we can identify a subpopulation of neurons which total contribution to the output behave like X1, X2, or X3. In this plot, I show how we found such populations. The key is that, both when there is a trigger and when there is no trigger, we can find in the reduced model a subpopulation of neurons with a null contribution to the output. In the reduced model, when there is no trigger, this subpopulation can be defined as a subset of neurons which receive a big enough input from V. Therefore, we define R12, the equivalent of the subpopulation X1, X2, as a group of neurons whose input weight from V is greater than 0.1 in absolute value. We can see on the H-plot that such subpopulation has a null contribution to the output when there is no trigger. So, not surprisingly, R3, the complementary of R12, defines a subpopulation equivalent to X3 when there is no trigger. Similarly, we can identify R23, the equivalent of the subpopulation X2, X3, with a criterion based on the weight from the trigger. This allows to identify R1, an equivalent of X1 when there is a trigger, and in the end, also when there is no trigger. And finally, it also allows to identify R2, an equivalent of X2 when there is no trigger. Let's summarize now what we have seen so far. First of all, in this work, we have proposed a model that can maintain information by implementing a gating mechanism. The model we propose is very robust to its parameters, and it suggests that this mechanism can be a generic mechanism used by any arbitrary population of neurons. By imposing the system to be open, and therefore continuously under the influence of stimuli, we have seen that a different solution than sustained activity can be used to maintain information. In our model, sustained activity is neither essential for decoding the memory nor for maintaining the memory. However, in the end, it is possible to reduce the behavior of the model in a 3-neuron model, where a neuron displays a clear sustained activity. To some extent, in the reservoir model, the sustained activity is implemented in a distributed way by a subpopulation of neurons. Moreover, if in the beginning we started from an unstructured reservoir, we can see that through learning, 2 functional pathways emerge, an updating feed-forward pathway and a maintaining loop. To conclude, let me remind that all these results are described in more details in our paper in neural computation. Also, I would like to add that an extension of our model has recently been accepted to cognitive computation. Without much details, the idea was to explore the latent space of the gated working memory model. We used a tool proposed in the reservoir computing community, Concept.org. Thank you for your attention.